everybody. I'm Dr. Debashish Giri, Program Coordinator in the Department of Information Technology, Maulana Abul Kalam Azad University of Technology, West Bengal. And this is the 11th session of the webinar series on cryptography, network security, and cyber security. That is jointly organized by Islamic University of Science and Technology. In our inaugural ceremony, we are having our Honorable Vice Chancellor, Sir, Professor Dr. Soikat Mitra. And we are having that eminent speakers, Professor Dieter Gullmann, Hamburg University of Technology, Germany, Professor Feng Hao, University of Warwick, UK, Dr. Ruxanda F. Olimint, University of Bucharest, Romania, and Norway University of Science and Technology in NTNU, Norway. So now I in our this webinar series, many eminent speakers already delivered their speech from different part of the world: USA, France, Belgium, Japan, Denmark, Australia, UK, Spain, South Korea, Switzerland, Germany, Norway, India, and so many countries. Now we are having the 3 invited speakers from the Germany, UK, and Norway. Now I request to our Honorable Vice Chancellor to inaugurate the session.
Okay, thank you, Dr. Giri. As I'm in a hurry, you can see I have 2 cords, one black and one white. That is for another program. So this is a nice thing that this is 11th in the series of the cybersecurity webinar. And it tells about this stupendous success of this webinar and popularity of this webinar among the learning community. And this should be because the cybersecurity now is one of the very fascinating, as well as very interesting, and as well as very critical, this of critical importance domain in this context. And we need to keep our cyberspace very safe. The cyber physical interactions, which is a part of this digital transformation in industries and all these things, in our all transactions, in our all endeavors, in our all efforts. So there, I wish this program a grand success. My request to Dr. Giri is kindly publish one compendium for all these 11 or more, if it is more in near future. Then compile all these lectures of all the experts. We are very thankful to all the experts who have come already to our these platforms for sharing their knowledges, and those who will be coming again. And now this will be a great this occasion for all our learners. And we believe that out of this exercise there will be a tremendous this interest and awareness will be created among the society, among the learners regarding this importance of cybersecurity, regarding all these emerging features of cybersecurity, and to embrace cybersecurity as a successful career in near future, as well as this as a separate branch of different branch of this academic and training program for our teaching community as well. So with this, I would like to conclude. My best wishes for all the learners. Congratulations to Dr. Giri and his entire team for organizing this webinar again and again for the benefit of learners. And my sincerest thanks to all these notable personalities in knowledge domain of cybersecurity for coming over here. Thank you.
Thank you, sir. Thank you for your valuable speech to the participants and the speakers.
Okay, so I'm leaving now. I'm attending another program. So my best wishes to all of you. Okay, so kindly continue.
Okay, thank you. Okay, thank you, sir.
Okay.
So now we are the first speaker, Professor Dieter Gullmann. Professor Dieter Gullmann received his diploma engineering in engineering mathematics in 1979 and doctor of technology in 1984 from the University of Linz, Austria, where he was a research assistant in the Department of System Science. He was a lecturer in computer science at Royal Holloway, University of London, and later a scientific assistant at the University of Karlsruhe in Germany, where he was awarded the Vinay Legendi for computer science in 1991. He joined Royal Holloway in 1990, where he was the first course director of the of the MSc in Information Security. He moved to Microsoft in Cambridge in 1998. In 2003, he took the chair for security in distinguished applications at Hamburg University of Technology. He was an adjunct professor at the Technical University of Denmark 2005 to 2009 and a visiting professor at Nanyang Technical University Singapore 2017 to 2020 and is a member of the advisory board of the Center of Doctoral Training in Cybersecurity at Royal Holloway University of London. Now he will speak today IoT and CPS security. Now I request to Professor Gulman, you are welcome to share your screen and start your presentation.
So, has the screen reached you?
Yes, sir, it is visible, sir.
Is it visible and audible also?
So, let's see. I guess I have to stay with this mode of the screen and cannot go to full display mode. It's a great honor to be here, speak in this webinar. The topic I've chosen is IoT and CPS security. I will explain the acronym should they need explaining in a moment. I will start with a quote from Virgil Gligor, possibly the first student to write a PhD in the area of security. In a talk he once gave, he was looking back at our field, IT security, computer security, cybersecurity, and observed it takes us 10 years from identifying a new problem, studying that problem, developing solutions, and after 10 years, we've reached a mature solution. During this decade, IT has changed. 10 years is a reasonably long time in our sector. So by that time, new security problems will have emerged, but researchers stick to their old problems and don't want to suffer the pain from moving on to a new area. Second background to this talk. Lots of colorful hot air balloons. This leads me to a remark on buzzwords. Buzzwords like IoT, CPS, if I may throw in blockchain, are meant to attract attention. They are multicolored, full of hot air, but also they raise a load. They are not well-defined technical concepts one can do meaningful research on. Now to my two acronyms, IoT and CPS. In my times in Singapore at Nanyang Technological University, I went to a talk by a visiting professor, Chinese professor active in the United States. She had been a project officer for the National Science Foundation, and made the comment, IoT, cyber physical systems, they really mean the same thing. IoT came out of the networking community. It means the internet working of things. Cyber physical systems came out of the sensors embedded systems community. So more hardware-oriented, computer-oriented. Both communities were observing the same development. Multiple devices, devices with sensors, devices with actuators contribute their observations to build new applications. I will structure my thoughts on IoT and CPS along the lines of communication, computation, and control. I will start with IoT from internet working. I have found explanation. IoT is the internet working of devices. I have found explanation. IoT connects devices to the internet. I see these two definitions not as strictly equivalent definitions. The first one has more the emphasis on devices that are being internet worked in some way. In the second definition, the focus is on connecting devices to the existing internet. IoT puts the focus on networking challenges. One popular challenge, communication protocols for resource-constrained devices, constraints relative to computational power, constraints relative to battery resources. I'm pointing you back to my first slide, Virgil Gligor's comment. Have we got security challenges, network security challenges that are specific to the Internet of Things? Here is a story I heard some 6 years ago. One of the largest cities in Germany. There is a single public utility run by the city. It operates the electrical grid. It operates the water supply. It operates public transport. The computer network that is now in place for controlling these different services use the same network. You have hence a network for the electrical grid and also for public transport. Ticket machines are connected to this network. Ticket machines are out in the countryside. I know this city. Out in suburbia, there will be lonely train stops with ticket machines. So you have terminals that are now actually also terminals for the electrical grid out in the public domain. In theory, someone could connect from the ticket machine, probably not through the ticket machine, but through a connection, but using the connection to the ticket machine and start playing around with the power supply to a city. It is a threat. What would be a solution? Proper network separation. Firewalls, to use the term, between the network for the electrical grid and the network for public transport. Is this a new challenge? Not really. Mid-1990s, firewalls were emerging as an item in the tool set of IT security professionals. My conclusion, this case study points to a matter of education, but there is no matter of research that needs to be resolved. In this presentation by this professor from the United States, she told her audience, more in the electrical engineering community, I understand you're eager to work on IoT security. It's an important topic, attractive topic. Funding possibilities exist. If you want to research on IoT security, don't start your search engine, type in IoT security, and look what you find, and then stop. Around 2000, there was wireless sensor network security. There was mobile ad hoc network security, looking at many challenges that today come under the umbrella of IoT. So her advice, if you don't review the state of the art, going back sufficiently long, your research applications will come back, hopefully I say, with reviewers remarking, you have missed the state of the art. However, also in the spirit of Virgil Gliger's remark, IoT might be a good excuse for keeping to work on old problems. We know how to deal with these issues. We can use the same ideas, put IoT in the title and the abstract and the introduction, and hope to get funded and hope to get papers accepted. In that respect, IoT is a colorful new balloon for floating old ideas. From communication to computation. The things in the IoT might send data to the cloud for the data to be processed further. You have smart things, smart devices, smart sensors that perform computations locally. To me, computation is the middle ground for IoT and CPS, security. When we talk about computation in the cloud, the natural security questions include if data are sensitive, how to keep data sent to the cloud confidential. You can go to cryptography. You will find useful tools, secure multi-party computations, homomorphic encryption, in general, privacy-enhancing technologies. Some of this predates the cloud. Today, when I'm reviewing paper for conferences, very often authors like to throw the cloud into the mix, hoping to make the work more attractive. What would be the research challenges? A major challenge I see is the design of cryptographic schemes that are efficient in real applications, not only in toy examples. To look at the trade-off between utility and privacy in real applications. I had been to a talk by a researcher from IBM Zurich, and in the discussion after her talk, she mentioned, we had access to a data set, patient data set, where machine learning methods can be used to detect early signs of diabetes. We know from medical research how life expectancy is statistically linked to the stage of detection. The earlier, the better. Final point, we did apply our privacy enhancing techniques to this data set until we reached a level of privacy that looked acceptable to us. But when we applied the machine learning methods to the process data set, the precision of prediction deteriorated in a way that the consequent deterioration of life expectancy had become morally unacceptable. This is research where one needs to go out of cryptography and has to understand the application domain better. As a comment on research directions, making big data privacy friendly is a topic of great current interest. Big companies, Facebook, IBM are working on it. I'm still aware of a number of research activities in Singapore at NTU going exactly in this direction. Continuing with computation. I once heard this story at a security conference. In the discussion after a talk, a gentleman stood up and said, I was the first in my town to install this advanced new heating system for my house. I was standing in front of the console and playing around, pressing on a plus increment button. And I kept pressing and pressing and pressing, waiting to see what happened. And eventually the system crashed. And the only way to get it back was to disconnect the console from power, wait a bit, and then restart the system. Hard reset. One might guess the reason for the crash, incrementing the counter, either led to a buffer overrun or to an integer overrun, and the program failed. This is not a new phenomenon. This is a nice early example to use in a course on software security, and it's not the first example of this kind that has been documented. I had been with Microsoft research in Cambridge when Bill Gates sent around his email about the security push. Some 20 years have passed since, and there has been plenty of research and also plenty of advances in practice to deal with software security. This research also applies to the IoT. You do not need new research to understand buffer overrun. You do not need new research to understand integer overruns, but you have to know about them and know how to write software that is not susceptible to this type of errors. Remark. Problem is that software for IoT devices is written by engineers without education in software engineering. I can vouch for that. I have been supervising computer science students doing project work with companies and heard from their managers in companies. We are all engineers. When a bachelor student comes in to help us writing our software, this is a major step forward for us. Further security challenges here: secure booting of smart things, attestation of the state of smart things, secure remote update of smart things. All are relevant challenges. All have been examined before, so they are not specific for the IoT. Before I move on to CPS, my view on what had happened in the past 40 years in this area of IT, networking, and so on. When network security started, when computer security started, there were areas of infrastructure security. Operating systems provide security services like access control, agnostic of application semantics. Computer networks transport data agnostic of application semantics. You will have heard, if you're in security, this definition, the security triad: security equals confidentiality plus integrity plus availability. This belongs to the 1980s. This belongs to infrastructure security. Now moving to cyber-physical systems. Ralph Lange, the gentleman who understood that Stuxnet was a worm intending to abuse industrial controllers, wrote, manipulations of a controller have less to do with the confidentiality, integrity, and availability of information, and more to do with the performance and output of a physical production process. So let's talk about control. In control theory, you have controllability. For any two valid states, A and B, there exists an input that takes the system from A to B. Observability, by looking at the output of a system for a period of time, you can identify, determine the state of the system at the start of your observation interval. And a third term from industrial control systems, operability. The system still performs satisfactorily, even if the conditions are not those the system had originally been designed for. In cyber-physical system security, I see control as the major issue. For security, CPS security, the fundamental question, how to maintain CO2 in the presence of an adversary. The goals of the adversary are not so much the goals of the network security adversary, confidentiality or integrity of data. They have to do with system state. Get the system state into a state the adversary wants to achieve. Make the system perform actions the adversary tries to perform. Attack methods. You could tamper with things, corrupt the system, corrupt the software. Stuxnet is an example. You could tamper with communication. We are back to the networking paradigm. You could also feed misleading inputs to the system. You do not touch the system. You do not tamper with communication. You make the system read wrong data from the real world and hence adapt its behavior accordingly. In terms of CO2, the goals of the adversary, raise CO2 for the adversary, reduce CO2 for the operator. The way to approach this topic, in my view, is do not look at CPS security, IoT security as infrastructure security. Look at the cyber physical systems as a control system for an application. And then my questions are, what has changed for the defender? What has changed for the attacker? What changes for the defender? You're up to malice rather than bad luck. Safety engineering has a long tradition and has a long tradition in dealing with random failures, random equipment failures. From a conversation in that community, we can predict the consequences of a single failure. Dealing with simultaneous failures already becomes tricky. I describe this as thinking forward. Here are two failures. What is the effect of those two failures? This is, in comparison, the easier question, easier than my next one. The next one has to do with thinking in reverse. That is the way the attacker thinks. Here is an intended effect. How can I manipulate the system to cause the effect I want? I'm still staying with the defender. What changes? Frequency of input changes. Observation, sometimes made. The way the systems are being set up, that sensors sample their inputs at a rate fit for safe operation, considering technical failures only. An attacker might change inputs faster if the attacker doesn't have to be physically present and can do these operations remotely. From a European research project, more than 10 years ago, if I'm correct, I heard from colleagues the following story. We were talking to Siemens, the German electronics company. We asked them, do you think we can destroy your valve with strange operations? No, no chance. It's designed to be a safe device. We were able to show to them that by rapidly opening and closing the valve, we were eventually overheating the valve motor, and eventually the motor destroyed itself. Effects in the physical world triggered by new ways of controlling an actuator in a cyber physical system. Still, what is new for the defender? Don't put too much trust into cryptography. Your adversary is not launching attacks against your infrastructure. Your adversary wants to deceive you about the state of your system. And this is not necessarily done while data are being transmitted. This can be done already before. There is a property called veracity. An assertion about an aspect relevant in a given application actually reflects reality. You have to do more than traditional IT infrastructure security. What could you do? You could use tamper-resistant sensors. You would rely on physical security, perimeter fences. I found this story on Bloomberg about an attack against a pipeline where one could see that the camera was hit from outside by a gun to switch off this control feature. You could correlate observed variables. You could compare variables with values predicted by your model of the system. And all of this depends on your specific application. A story without slides. 10 years ago, roughly, I had a student with Volkswagen, the German car manufacturer, and he told me we were looking at different ways of observing the speed of a car. GPS coordinates to track how fast the car is traveling, wheel spin to observe how fast the car is traveling. And we were aware of a situation where the wheels are static, but the car is moving. This is a situation where your car is being taken from the place you have left it, either because you've left it in a no parking zones or because someone is stealing your car and has pulled it on a truck to drive away with it. Someone from the audience said, and there is the converse, the wheels are spinning, but the GPS data tell you the car is not moving. Your car is on a test stand. And if you followed Volkswagen's history, they had been using methods for detecting whether a car was driving or whether a car was being tested and to control the configuration of their engine accordingly. And their attempts had not worked out in their favor. Consistency checks compare assertions from a sensor with related assertions with maybe data derived from a digital twin. I call the devices making the observations, making the assertions, witnesses. Consistency checks rely on several witnesses being available. Security relies on the assumption that the adversary is unable to corrupt a sufficiently large number of witnesses, and you are getting closer to research on reliability, Byzantine fault tolerance, designing solutions on the basis that some, but not all inputs are corrupted. In safety engineering, it is common to assume statistical independence of failed devices. If you look at security problems, this is a dangerous assumption to make. Colluding witnesses may make false statements. Security proofs can be based on assumption that only a limited number of witnesses is compromised. If the attacker is able to form coalitions, you do not get a lot of security. If you have ways of choosing your witnesses in a way that, for example, they're picked at random, for example, they're picked on something derived from hash values of what you're currently trying to observe, then it makes it more difficult for the attacker to know in advance which of the sensors should have been corrupted to provide wrong inputs. You have further examples in location services. GPS. You will find in the literature several interesting papers on fooling the GPS receiver about its true location. Keyless car entry is an interesting area. I had once been supervising a student with a company here in Germany where the car had 2 sensors to locate the position of the key and was able to detect whether a key was really where it ought to be to open a car. In wireless LANs, you have location services using round trip times to construct virtual maps, synthetic coordinates. All of this can be compromised by manipulated inputs, wrong round trip times, jammed beacons, fake beacons. The research area on the bottom of my diamond, I have trusted tamper-resistant devices. That is the easy way out. You assume that somebody else will have solved your problem. You have witnesses, or you have witnesses corrupted at random, or assume that corruption happens randomly. That puts you into the world of reliability and fault tolerance. You have the most powerful of fault models, the Byzantine fault model. Then you can look at Byzantine fault tolerance. And the interesting research direction for me at the top, independent witnesses that observe dependent features. Can we achieve more security than with random corruption? Can we achieve more efficient solutions than Byzantine fault tolerance? What's new for the attacker? Physical impact. My PhD student on CPS heavily objected to remarks. An adversary who gets access to the network can do whatever he wants to do. Her point was the adversary may be able to create any traffic he wants, but does he achieve the physical effect on the system he wants? To do that, the attacker has to understand the system and the attacker's goal, achieve controllability. From her book, a brief story on communication in a cyber-physical systems in the domain of physics. It's phrased in industrial control system with zones that group assets with common security requirements. Zones communicate via conduits, a pass for the flow of information between zones. To secure industrial control system, secure the conduits, one of the research strategies. The example, a piping infrastructure in an industrial facility, devices related physically. Then these physical processes can become conduits. If you're able to influence one device via physics from another device, your IT security that separated the different zones will no longer be effective. So a proper security zoning analysis must also look into the physical processes that connect components. You cannot get rid of the processes. They're here to make the system work, but you might get a better understanding how to monitor those processes. Here is her examples. 2 PLCs connected through a pipe containing a liquid, different networks, segments, properly separated. In the attack, no electronic communication between valve and pump. Goal of the attack, again, as in a story I mentioned before, damaging a device. The attack uses the valve position to generate bubbles, cavitations. And these bubbles, or to create bubbles, the bubbles will then have physical impact on the metal they hit and eventually wear out the metal. That is from Marina's talk at Black Hat 2017 on evil bubbles. This is a lengthy process. The attacker has to stay below radar for a long time, might then also spoof some sensor readings, flow sensor readings, so that the system operator is not aware that strange things are happening in this particular pipe. If you have additional sensors, vibration sensors, temperature sensors for the pump, you might be able to use those data to see that your system is not behaving in the way the sensor readings suggest to you. In terms of trusted sensors, you might be justified in assuming that analog sensors that are only accessible locally can be trusted. Coming to the end of my presentation. The way ahead for us in the research community. Fail-safe systems are built to shut down in an orderly way when they're brought into an abnormal state. If you manipulate the system randomly, it will probably shut down, but as an attacker, you will not destroy the system. As an attacker, you must understand the process that you are attacking. If you're trying to create a better understanding by developing a model of the system you want to attack, but also as a defender, if you want to understand what might happen to you, you will need a model of system behavior outside normal operating system ranges. The experience we had made when we were talking to chemical engineers in our university about a process we are interested in, we do not have a model in that range anymore. For them, it was no longer relevant. They wanted to control the process proper. So that creates also a new challenge for the application domain to understand their security, to understand the impact of cyber attacks on their system. They might need more wide-ranging models of the system. As an attacker, you have to know the controls that can be manipulated. You have to know the sensors that you may manipulate to change the state of the system. You need a good model of the target. I've just remarked, might need a more comprehensive model than required by the operator. Might need reconnaissance, which has to do with observability. I've mentioned the obstacle course on the previous slide. The attacker has to bypass built-in safety measures. So it's an issue of controllability from the adversary's angle. can I control the system to do what I want to achieve, given the system is constructed as it is, and that I'm not doing what the system expects me to do? Bypassing built-in safety measures might be easier for measures in cyberspace, but here I'm speculating. It's also important for the attacker to keep flying under the radar and make it difficult for defenders to pinpoint the cause of disruptions caused. In terms of CO2, the attacker's goal, reduce observability for the operator. Where are we now in research? Still at the beginning, although workshops on CPS security have been running for roughly 5 years. There are a few incidents like Stuxnet that keep being brought to the table to explain why CPS security is so important. Analysis by experiments and simulation, yes. Experiments on real systems, no. Experiments on test beds with limitations. I also have contacts to SUTD in Singapore. They ran a few capture the flag experiments on their CPS test beds, but with restrictions on what attackers were allowed to try. You do not want, within the scope of such an exercise, to destroy your expensive infrastructure. The nice, coherent theoretical framework for CPS security does not exist yet. Where to move to? Go from simulations to adversarial control theory. This is a term I'm suggesting. The question now becomes how to take a system out of the operator's control into the adversary's control, although safety measures are already present that try to obstruct the attacker. And I see more similarities to software security. I see more similarity to hacking into a software system to get it perform actions the designers never had in mind than to cryptography. I call it also safety engineering in reverse. It's a new mode of thinking, and that's why people who have not brought up in security find this a huge obstacle. It requires expertise in control theory, in the application domain, and in thinking about weird machines. Weird machine is again a term from software security. So to make progress, we have to step out of our world, established world of IT security, better understanding of the applications, and when we move into the engineering domain, better understanding of control theory. With this, I'm at the end of my talk and quote another eminent professor, the late Jim Massey, the difficult problems are those that nobody is working on. Thank you very much for your attention.
So, participants, you are having any question?
Participants, if you have any question, please put it in the chat box. Sir, we can find that there is 2 questions.
I cannot see the questions
Sir, one is
yet.
one
I
in chat
guess I
box.
have to stop sharing the screen.
Yes, sir. So first question is from Piali Karmakar. The question is, sir, how can we secure an IoT device as all devices are interconnected?
Securing the device to me has nothing to do with securing the communication. Securing the device means the software that receives inputs via the connection is able to handle malformed inputs. This is first an issue of software security. Writing proper passes, not having buffer overruns in your software, not having integer overruns in your software. Securing the device can also mean if you want to do remote updates, do it in a secure fashion. There are protocols, cryptographic protocols that support this. And I know, for example, in the medical domain that companies here in the area have, for a number of years, been looking at ways of doing that. There was a question on Q&A I just saw, can we secure the communication? Of course you can secure the communication. But if the data you are transmitting is already malign, then you transport your, or malicious, then you transport your malicious data to the device and it takes its effect. Protecting communication goes some way, but it does not protect the device. It protects communication. It makes it, for example, impossible to manipulate data in transit.
So any more question from the participant end?
Sir, in the chat box, the reply is that, I mean, sir, can't we secure the data transferred? Sir, please see the chat box.
Yeah, of
Yes.
course you can secure the data transferred, but this is only part of the problem. If the data that is being sent is already malicious, it need no longer be changed. It need not be protected. It's already damaging. So yes, you can secure the data, but you also have to look at the end systems. And if one end system sends malicious data to another end system via a secure channel, you still have an attack. I see a question about IPv6. I don't think I'm not an expert in IoT, but I cannot believe that they still will use IPv4 to a great extent, unless they have their own local network. And with IPv6 addresses, I haven't thought about this issue, and I do not see any immediate answer why differences in IP addresses would have a great impact on how the Internet of Things work. Only if you use IPv4, you will do it probably in your local network and have gateways to the outside world, because otherwise you will be running out of addresses pretty quickly. If you have IPv6 addresses, you can have globally routable addresses for all your devices. And that raises the question, how well can your device protect itself from the world? If you hide it behind some gateway, this question is less urgent.
So if there is no questions, then thank you, Professor Bullman, for your nice presentation.
There is just a question about. Yeah, sorry. So just a question about my email. You just have to Google for my name or to ask Dr. Giri, and they can help you most certainly. Thank you very much for your attention.
Thank you very much for your valuable speech. From your busy schedule, we are able to speak in our audience. That is what our thankful regards to you. Our hearty gratitude goes to you, Professor Rogelman. So, if you are organizing such type of event in future, we also again contact to you. Okay. Thank you, Professor. Thank you, sir. So, our next speaker, Professor Feng Hao. Feng Hao is a professor of security engineering and head of the system and security research teams at the University, at the Department of Computer Science, University of Warwick. He received his PhD in 2007 in computer science from the University of Cambridge. Being a security engineer, he has a mixture of industrial and academic experience. Prior to starting his academic career, he worked in the security industry for 6 years with colleagues. He designed a few cryptographic protocols like AVNet, OVNet, JPEG, YAC, DRI-IP, and Shell, some of which have been used in real-life applications. In particular, JPEG has been adopted by the threat group as a de facto standard to perform the IoT communication process used in Google Nest, ARM, etc. An internationally standard in ISO IEC 11770 version 4, DRI-IP has been successfully trialed in Gateshead during the UK local elections on 2nd May 2019. His first paper during PhD on combining crypto with biometric effectively IEEE transactions computer 2006 is ranked the top in Google Classic papers in the category of cryptography and computer security. He worked on self-enforcing e-voting, has led to a 1.5 million ERC starting grant and an ERC proof of concept grant. He will speak today ACL shield-based auction without actionary. Now I request to Professor Feng, you are welcome to start your presentation. Feng, Feng, you can start your presentation.
Okay. Thanks.
So how are you? How are you, Feng? Feng, how are you?
Nice
So long time back, we are in on the face to face.
Yes. Let me try to share my screen now. Can you see my slides?
Yeah. It is visible, Feng.
Okay, great. Okay. Yeah, so thanks for the introduction and also invitation by Basis Giri. It's really my great honor to give a talk here. So I'm going to talk about verifiable e-auction without auctioneers. First of all, I would like to acknowledge that this is a collaboration with my colleagues, Samuel Beck, Siamak, Shahan Dashti, and Engineer Ray. In fact, two of the authors here are from India. They are from West Bengal. So there's an interesting connection here. This is a result of a different project. In that project, we worked on e-voting, verifiable e-voting, and how to make the system self-enforcing without involving trusted tallying authorities. It turns out that in security and in cryptography, many different problems are interconnected. So you have one solution to one problem, then there's a good chance that you find the solution could be applied to other problems. And that is what's happening here. We find that the solutions we designed for verifiable e-voting could also be adapted to solve auction problem. So that was unplanned and unintended, but that turns out to be one of the most interesting results from the e-voting project. First, quick introduction about auction. I think everyone knows or heard this auction or participate in the auction process. This is basically a way to allocate resource based on competition. If you have something to sell, then you sell it by auction. And that there are two types of auction here. One is open cry. So for open cry, everything is open. You have an item to sell and everyone just shout how much they are willing to pay. You can start with this, you can start the price from the low price and then increase it until the last person who is willing to pay. So that would be English auction. Or you could start from a very high price and you reduce the price until the last person who is willing to pay. That is called Dutch auction. The other type of auction is more interesting, is from the security perspective, is called sealed bid auction. So for sealed bid auction, everyone put their bid price in a secure envelope. So no one see others price, and then you reveal the price, and then see who is winner. Because the bid is sealed, so it has this privacy aspect. So that makes it interesting from the security perspective. In this talk, I'm going to focus on the sealed bid auction. In the sealed bid auction, there are also two types of auction schemes. One is first price sealed bid auction. This is most straightforward sealed bid auction. So everyone bid for an item, the highest bidder is the winner, and then he pays the highest bid price, very straightforward. The second type is slightly more counterintuitive. It's called second price sealed bid auction. So in this case, the winner is still the same. So whoever got the highest bid, then is the winner. But he pays the second highest bid price. And this auction is called weekly auction. This was named after William Weekly, who first developed theory for this type of auction scheme. And in 1996, he won a Nobel Prize for his contributions on auction and economics. So that was just 3 days before he passed away. He was still eligible for the Nobel Prize. So weekly auction, this is extremely important in the field of auction. You will see lots of studies on this auction scheme. The very attractive feature of this auction is that it has been proved by Weekly that this is strategy proof. In other words, if we assume all the values are evaluated in private, so the bidders, they evaluate the items in private, then the best strategy for the bidder is to bid their true evaluation. And that is very powerful result. Unfortunately, although weekly auction is extremely important in the auction field, it actually has rarely been used in practice. You don't really see it used in real life applications. And why is that? We can see an example to see why. Here we have one simple auction example. So there's a trusted dealer, and we have 4 bidders. Everyone seal their bid price in an envelope. So apparently, here we can see that Dave is the winner because he has the highest bid. And he should pay the second highest bid, and that is £3 million. Very straightforward. However, if you do it electronically, there are the 2 problems, or either electronically or physically, the 2 problems. The first problem is secrecy. In this case, the trust dealer sees everything, and he knows what the bid in the envelope. This has privacy and other issues, especially for the weekly auction. Remember, the best strategy in the weekly auction is that everyone bid the item based on their true evaluation. And this true evaluation is a reflection of the market intelligence and other the financial station of the company. So that is a trade secret. You don't want this trade secret to be known by other people. But in this case, the trust dealer knows everything. The second problem is integrity. When the auction is finished, if the trust dealer tells you that the second highest bid price is £9 million, and the winner, you should pay £9 million, how do you know this is true? You cannot ask dealer to open all other envelopes because that will be a compromise of secrecy. So you have to trust the dealer. But in this case, the dealer gives you a wrong amount so that the dealer may get some extra revenue. So that is a fundamental issue with a dealer. In this case, the dealer is a trusted third party. So everyone should trust the dealer. A classic definition in security is about trusted third party is by Ross Anderson. It says a trusted third party is a party that can break your security policy. Slightly counterintuitive to people who are not in the security field, but let's support on definition of trusted third party. If you have a party that you trust completely, then that party is the one who can totally break your security policy. So indeed, in the field of security research, the motivation is to address this trust issue, get rid of the trusted third party if you can. So that is the main motivation for over 25 research, starting from 1996, and the first paper by Franklin and Rater. And after that, a large amount of e-auction papers have been proposed. However, if you read those papers, you will find that almost all of them, they follow the same approach or the traditional thinking in the auction process, that you need to have a trustworthy auction in the physical auction application. Then you should also have a trustworthy auctioneer in the electronic equivalent. And then the question is how to distribute the trust on this auctioneer. The solution is by using threshold cryptography or MPC, and that is pretty standard technique. If we look at the previous solutions, we can summarize these solutions into 2 different categories. All these solutions have been published at top venues in conferences, in journals, but they all basically follow these one of the 2 approaches. The first one is, instead of trusting one auctioneer, you trust 2 or more than 2. So you distribute trust to several parties. The second approach is that instead of trusting one auctioneer as a trusted third party, you involve other trusted third party, for example, a party that generates randomness, and you assume these extra trusted third parties don't collude with auctioneer. So they are similar in concept, but all of them have the common issue that you have to assume all these trusted third parties must not collude. If they collude, then they can still compromise your system. So this address the trust issue to some extent, but it doesn't really address the key issue. Here, there's one obvious question for people who work on multi-party computation. And you may wonder, we could simply apply multi-party computation to solve this problem. So for those who are not familiar with multi-party computation, I'll just very briefly introduce multi-party computation. This is a framework that you have multiple parties. Everyone has their own input, secret input, xi. And you can define this multi-party computation, any arbitrary function f, so that everyone will learn the output of this function, and they don't learn anything else. And you can have the MPC framework such that it works with arbitrary function. If you follow this definition of MPC, then you may wonder that the solution is trivial. We simply apply this MPC to a specific function, and the function is max function. Given a set of input, this function should tell you the maximum of the input. Very straightforward. Then we solve the problem. But in security, if you think something is simple or too easy, then you have to be extra careful. In fact, here, this is actually a complicated issue. So I'm going to illustrate a little bit more. You don't really see the concrete solutions people use MPC to solve this problem. And there are limitations with MPC. So typically, usually the limitations come from the assumptions in the theoretic construction. So typically for MPC, you have this assumption: everyone should have pairwise secret channels with everyone else, in addition to a public authenticated channel. Then the question is, how do you set up these pairwise secret channels? That is one issue, but a more important issue, which is not really explained in many papers, is that once you have these secret channels, then the protocol is not publicly verifiable. And why this public verifiability is important? If I'm the seller, I trust this network to do the auction for me, and I want to verify whether the process is trustworthy, the data has been accurate, and the revenue I get is the actual reflection of the whole process. I will need to verify the data. But if this protocol involves secret channels, then I cannot verify data. So that is actually a fundamental limitation. And the second is that for many MPC protocols, they assume the honest majority. This is because the general MPC framework was extended from the two-party secure computation from Yao's initial solution. Once you extend this two-party relation to multi-party relation, then naturally you require this honest majority. But in reality, if you have 3 players, then you require 2 to be honest, but it's not impossible for an attack to compromise all 3. So far only theory. Let's look at one practical example. There was an application of MPC to solve the auction problem published in 2006. This is one of the few examples of using MPC for the public, for applications in the public. And this is, in fact, one of the celebrated events in the MPC field, that you use MPC in the real world application. So this example gives us insight how the MPC is used, but also see the limitations of MPC. So here we have 3 parties to do the auctioneer. And so 3 parties here, and so this is for the auction sale of the sugar beets in Denmark. The 3 parties, one of the party is the association of the farmer, and the other party is association of the customer, and the third party are the researchers of this paper. And you assume these 3 parties are independent, so they don't collude, or at least 2 of them are honest. Each party generate a key pair with public key and private key. Because you only have 3 parties, so they can physically meet and exchange the public key so that they could have a secure communication. If you have more parties, then you will need a PKI to establish the secure communication between the three. All the bidders encrypt their bid and send to the auctioneers, and then the auctioneers apply MPC to solve this, to compute who is the winner. So this is how it was designed and how it was implemented and deployed in the 2006 auction. If you look at this example, and you will see that this is not strictly an application of MPC on the classic MPC setting. In the classic MPC setting, this should be a decentralized setting. Everyone provide input, and everyone should learn nothing more than the output of their function of MPC. But this is not the case here. This is a centralized system. Everyone provide this encrypted data to the auctioneer. And the auctioneer, 3 auctioneers, they run the MPC so that they don't learn anything beyond the output of the function. So this is not really the classic setting for MPC. So that is actually something we should take care of. But you can see the example of using MPC at least to distribute the trust between from 1 auctioneer to 3 auctioneer. But MPC is not only way to do it. You could also use threshold cryptography or secret sharing, or all these techniques. They may have different names, but they do basically the same thing. So a fundamental question here is that, is it possible we can do the auctioneer in a decentralized setting so that you don't really need to trust any trusted third party or auctioneers? The quick answer is yes. And if you remember, in the first part of my presentation, I mentioned this OpenCry. So you could have an auction scheme similar to the OpenCry. You have all these possible bid price. So you simply exhaustively encrypt all the bid price. And then you have this, for example, you could have this OpenCry approach. Everyone announces their encrypted bid, and then they release, then they reveal this encrypted bid each time for each round. So this could work, and you have your privacy because every time you only reveal 1 encrypted bid in each of the rounds. But this trivial method will give you exponential complexity. For all the possible bid price, for example, for an item from £1 to £1 million, you have to encrypt from 1 to 1 million these other possibilities. And that will be exponential complexity for 2 to the power C. The C is the bit length of the bid price here. So that is not efficient. And in fact, the similar idea have already been proposed by some researchers, especially Brent Wu in early 2000. So they want to get rid of the auctioneers, and the way they propose is by essentially encrypt all the possibilities of the bid price and do a similar kind of OpenCry approach. But that will give you exponential complexity for the computation and for the rounds. That is too inefficient to be practical. So here, what I'm going to explain is that actually we can have an efficient solution with a linear complexity. And that is probably the best you can achieve. So this would be the communication setting in our solution. It's totally decentralized. You don't have a trusted auctioneer, and we don't have secret channel. Everything is public. Because everything is public, you could use, for example, Ethereum as one public bulletin board. So everyone just encrypts the data and publish on this Ethereum, and then we could have a smart contract to do the computation to compute what is highest bid price. So this is the classic setting for MPC. We don't involve any auctioneer, any trusted third party. So it's totally decentralized. The only person you trust is yourself. So for this construction, it will involve some primitives. If you look at some previous MPC techniques, they usually involve quite a few primitives, such as addition, multiplication, and some other primitives. And for each of these primitives, you have this gate, and you construct a circuit with all these gates combined together in a complex way, and then you have multiple parties to evaluate the gate. Here, we also have a circuit, but the circuit is extremely simple. The circuit only has one gate, precisely one gate. And this gate is Boolean OR gate. So this is actually, to us, is amazing. You don't need this complex circuit. You just need one gate, but you design the input of this gate in a special way that with simple one gate or Boolean OR gate, you can achieve quite amazing result. So this primitive is Boolean OR, and some people also call it anonymous vetor. This is essentially the same thing. Everyone has one binary input, and you want to compute the Boolean OR of these inputs. So this is a study, this is problem. Actually, we looked at this problem many years ago, more than 15 years ago. So when is in fact the first problem I looked at when I was a PhD student. So around 2004, that was still during the time of this Iraq war. If some of you may remember, George Bush made this famous speech in the United Nations that he proposed to attack Iraq, and he asked people to take a vote. If you are agree, then you are with Bush. If you are not agree, then you are with the terrorist. He doesn't give you middle ground. So when I saw this news, I thought maybe there's an interesting problem here. What if I don't agree with you, but I want my privacy? I don't want you to know that I don't agree with you because I don't want to offend you, and I don't want to be penalized by you. Is it possible? I can say no, but you don't know that I said no. So that is actually the anonymous vetor or the Boolean OR problem. So together with another PhD student in computer lab, Piotr Zielinski, he now works for Google. We thought this is an interesting problem, so we worked on a solution. And it turns out that this solution is extremely simple, only 2 rounds. But don't be deceived by the simplicity here. Designing a simple problem is actually the hardest challenge in security and in cryptography. It's so easy to define a complex protocol, but it's extremely hard to design a simple protocol. So in this case here, we have a simple protocol, only 2 rounds. In the first round, everyone publish a random public key and zero-knowledge proof for the public key, such as Schnorr signature, to prove that you know the exponent, or in other words, this public key is not a random string, but a proper public key. Then you compute this g to power yi. This is you can compute this is a simple multiplication and the subtraction and the division of other public keys, and everyone will be able to compute this g to power yi. You don't need any secret keys. In the second round, you raise g to power yi to a value. You could raise it to the power of xi if you don't want to veto, or you raise it to the power of a random value if you want to veto. After the second round, then you simply multiply this g to power ci yi. If the result is 1, it means that no one has vetoed. You have achieved a unanimous agreement. If one of them has vetoed, then you get a random result, a result which is not 1. So you know someone has vetoed, but you don't know who. So at the time, we compare this with other techniques. And we find that in every aspect of this efficiency, this is more efficient, and in fact is close to the best you can achieve. Only 2 rounds linear computation and linear bandwidth. This is really the best you can achieve. So that was back in 2006. At the time, it was most efficient. Today, 2020, this is still the most efficient. However, there's one interesting property about this about this protocol. We call it Vitor's advantage. So in this protocol, the Vitor can learn one extra bit. The extra bit is whether or not he's the only one who has Vitor. Apologies. So he knows this extra bit, but he doesn't know who the identities of other Vitors if they exist. So there's one interesting question: is this a bug or a feature? We argued this is whatever it is, but it doesn't compromise privacy. So we acknowledge this in the original paper. To see why you have this extra information, this is something fundamental to the two-round protocol. Two-round is best efficiency you can get for multi-party computation. If you are the Vitor, for example, in the second round, you raise it to the power of R, and then you finish this two round. But you can always simulate round two by raising to the power of xi, and you know the value of xi. Then you know whether or not other people have waited. So this is how you get this extra 1 bit information. But this is only 1 bit. You don't learn anything else. So we explained, and in fact, if you look at some other papers, they have some simulation, but not explicitly explained. So we made explicit that you have this extra 1 bit. So that was in 2006, and today we looked back on this 1 bit, and we found actually, to our surprise, this is very, very useful. And that actually changed our understanding about this MPC or theoretic model of this MPC completely. So I will explain more why that is the case. Here we have two secret definitions. The first one is inclusive privacy. So that is a generic definition for MPC. In other words, everyone should learn nothing more than the output of this function. This is the best possible you can get. And we introduce another definition. So for this definition, that so everyone still learn nothing more than the output of this function, but we allow each party to learn some extra information. But however, we limit this extra information to a function with the input. With the input of the participants, excluding the malicious players. If you are the only player in this network, and then you learn the output of a function that exclude your own input. So so in this definition, we allow the participants to learn a little bit more information, but this information is limited. And I will show that this actual learning of the information is crucial. Now we are ready to describe this protocol. So we call this SEER, or self-enforcing auction lot, named after animal because we love animals. This is based on one simple primitive, the one simple gate, the boolean OR function. In the protocol, we actually use a modified this anonymous Vitor, but the complexity is still the same. We need to modify it so that the zero knowledge proof will work within this context. It has two phases. The first phase is commitment. So everyone, they encrypt the bit price bit by bit, and it's published on a bulletin board using algorithm encryption. This is standard technique, nothing fancy here. And we also publish a zero-knowledge proof for each of the ciphertext to show that the data you commit is either 0 or 1, but it doesn't reveal anything beyond that. So this is standard technique. The second phase is bidding phase. This is the core and is everything about, is a whole specification of the auction protocol. Usually auction protocol is very complex if you read other papers, but here, everything you need to know is on one slide. So it's extremely simple. It has two stages. In the first stage, essentially everyone does voting from the bit by bit, and they start from the most significant bit. Let's look at the first bit, the first bit position. So each bidder, they choose a private input Dij here. And the Dij is input to this Boolean OR gate. The Dij has to satisfy this zero-knowledge proof statement. So this is the statement. Essentially, this statement says, if the commitment is 0, the Dij has to be 0. If the commitment is 1, then Dij has to be 1. In other words, you have to use the same input as the bit you commit in the previous phase as an input to the Boolean OR gate. And then everyone compute the Boolean OR of this bit position by using this Boolean OR gate. If the output is 1, that means someone has provided input 1. Then we call this bit position a deciding position. We call it deciding position because potentially we have a winner because someone has used 1, has supplied 1 at this position. We use this J with little arrow bar to refer to the previous deciding position before this I position. When the Boolean OR gate is 1 for the first time, then we should move on to the next stage. In the next stage is exactly the same. Everyone provide input to this Boolean OR gate. The only difference is that the input now has to satisfy a slightly different zero-knowledge proof. So this is a statement of the zero-knowledge proof. This is actually the key for the protocol. What this zero-knowledge proof essentially say is that it depends on your input in the previous deciding position. If in the previous deciding position, your input is 0, because it's deciding position, so someone has provided input 1, but your input is 0, that means you have lost in this auction race. And according to this zero-knowledge proof, if you provide 0 to the previous deciding position, then for all the subsequent bit positions, you have to use 0 as input to this Boolean OR gate, regardless what you have committed in your previous commitment. On the other hand, if your input to the previous deciding position is 1, that means you are still in the race. You are potentially the winner, but we don't know because maybe there's another one who provide another person who provide 1 in the previous deciding position, but potentially you are still in the winning race. So when this Dij left bar is 1, then you get exactly the same statement as previous one. So you should still use the same input as a commitment as an input to this Boolean OR gate, and you continue towards the finish of this protocol. So this is a whole specification of this auction process. The key with this auction process is the 2 zero-knowledge proof statement. The first one is straightforward. The second one is a little bit long intuitive, but the second zero-knowledge proof statement is a key to this protocol. And we don't need fancy zero-knowledge proofs. We just use standard zero-knowledge proof with AND and OR statement. So nothing fancy with a zero-knowledge proof, but the new thing here is how you construct this zero-knowledge proof in a special way that you can compute the output in the way you want. So let me give you one example. Hopefully that will make it clear. We have 3 bidders here. 1, 2, 3. The first bidder has the bid price 01010. Second bidder is 01001, and the third one is 00111. Apparently, the highest bidder is the first one because value is the highest. So in the first round, every bidder simply commit their bid price bit by bit on the bulletin board. The first one is 01010. This is all encrypted by using a gamma encryption. And then in the second stage, you do this voting bit by bit, bit by bit. You start from the leftmost bid position, that is the first bid position. What you do is that you provide input. The input, according to the zero-knowledge proof, has to be the same as a commitment. So in the first bid position, the bidder 1 use 1 as input, and second bidder use 0, and third bidder use 0 as the bid position, as a bid value to the Boolean OR gate, and you compute the value of this Boolean OR gate is 0. You stay in the first stage. In the second bid position, the first bidder and everyone use the same input as their commitment, so 110 here. Now the Boolean OR gate gives you output 1. So 1 is a deciding position. So that means potentially we have winner and we have loser in this bid position. Because this is 1, now we move to the second stage. In the second stage, for the first bidder, because of previous bid position, he used 1, so he's still in the race, and he used the same bid. He used the same bid as the commitment, so that's 0 is the same for the second bidder. But for the third bidder is something interesting here. Although his commitment is 1, but because he used 0 in the previous deciding position, it means that this bidder has already lost. So the only way he can satisfy this zero-knowledge proof is that he must use 0 as input to this Boolean OR gate. But other bidders, they don't know. They only know that this input by the bidder 3 satisfies the zero-knowledge proof. And we compute the Boolean OR gate here is 0. So we move on to the next stage for bidder 1. Because bidder 1 is still in the race, so bidder 1 use the same input as commitment, so that's 1. And for bidder 2, that's 0. For bidder 3, again, because he has lost, he has to use 0. In the last bid position, bidder 1 use 0. For the bidder 2, because the bidder 2, he used 0 in the previous deciding position, so it means that bidder 2 has already lost in the previous deciding position. According to the second stage zero-knowledge proof, he has to use 0 as input to this Boolean OR gate. And then the same for bidder 3. Now you get the output 0. If you concatenate all these output, what you get? You get the output 01010. And that is precisely the value of the bidder 1. And that is the highest bidder. We have the efficiency analysis. You can read paper. What I want to highlight here is that the computation for the bidder. So we separate the computation in 2 aspects. One is computing the subtext, and the other one is to verify the subtext. It's good idea to separate the 2 because in the implementation, if you, for example, if you use Ethereum blockchain as a public bulletin board, and then subtext or the zero-knowledge proof will be automatically verified by this blockchain. For the computation by this bidder, this is linear to the bid price, the bid length C. You can see that there's no n here. N is the number of bidders. Even you have more bidders, the computation load, it doesn't increase. So this makes this solution highly scalable, even for a large number of bidders. The computation cost stays constant and only linear to the bid price. Of course, for the verification, you will need to have this end term, but the verification is done publicly, and that could be done by this public bulletin board. It's similar for the communication bandwidth. So you can refer to the paper for the proofs, but here I just want to highlight some important results. The first one is we can guarantee this auction scheme gives you the correct maximum output. Here is a sketch of the proof. The key here is zero proof in the second statement. So for this second statement is equivalent to this form. So essentially, this depends on what is the input, the bidder's input to the previous deciding position. If the previous deciding position is 1, then you should use the same bid as a commitment. But if your previous deciding position is 0, that means you have already lost, and you must use 0 for all the subsequent bid positions. So it doesn't interfere with the subsequent computation. And if you follow this zero proof, then it's very easy for you to prove that the output you get is the maximum of the process. The privacy, you can prove that this satisfies the exclusive privacy definition. So everyone should learn nothing more than the output of the function. And if you have a collusion of players or malicious players, then the malicious players will learn nothing more than the output of the function with all the input, excluding the malicious players' own input. So what this essentially means that if you want to guarantee privacy, then you should have at least another bidder who is honest. The idea with privacy is that you hide in the cloud, and you need to have at least another honest bidder. This is a reasonable assumption. If you think about in most MPC techniques, you require the majority of the players to be honest. But here we only assume at least another bidder who is honest. So here, one question is that we have already shown that you can achieve this exclusive privacy. Is it possible we can achieve the inclusive privacy? Because that will be like the standard definition in MPC, or so far the gold standard in MPC. The answer is yes, and it's very easy to do that. We simply change the Boolean OR gate to a different gate that satisfies the inclusive privacy. And we already have techniques to do that. If you use a Boolean OR gate that satisfies this inclusive privacy, then the overall the auction scheme will also satisfy the inclusive privacy. But however, probably surprisingly, you will end up with a scheme that is less useful and less practical. That is probably surprising, especially for purists who work on cryptography, that you have a scheme that can satisfy the generic definition of privacy, but you end up with something which is not very secure and not very useful. Why is that? When we design security systems, we cannot just design the system within this frame theoretic context. We have to put it into a practical context. And the practical context here is auction. So we need to consider several practical constraints. The first one is time. What happens when you have a number of participants who have the same input? You have to address this. If you have this auction scheme with a generic auction scheme so that everyone strictly learn nothing more than the output of this maximum, then there's no way for you to know whether or not there's a tie. This is by the definition of this. If you simply design the theory, it's fine, but you cannot use it applied for practical applications such as auction, because for auction, you must know if there's a tie. But for the exclusive privacy, we can easily resolve this tie. And also adaptive, when you know that you already have a winner in the first bid position, then there's no point for you to do the following computation. You can simply stop there and you announce the winner, and the winner will reveal their commitment. So that will save time and also computation. But this is not possible with inclusive privacy by definition. But that is doable if we have exclusive privacy. And also the third reason is very important, is we consider weekly auction. How do we extend this to support weekly auction? Assume we have a generic MPC protocol that limits you to learn nothing more than the output of the max function, and the protocol is publicly verifiable, doesn't provide any, doesn't require any secret channels. So you can have this protocol in the most perfect and theoretic sense, but now how do you apply it for auction, for weekly auction? The only way you can do it for weekly auction is that you apply this protocol to get the maximum bid for the first round, and then you exclude this maximum bid, and you run the protocol twice, second time, for the remaining bidders to get the second highest bid. But then the highest bid is trivially revealed, so everyone knows the highest bid, and that is totally unnecessary. And that is a straightforward breach of privacy. So as you may see here is that you have a seemingly perfect solution, but when you apply it to weekly auction, you end up with something which is trivially insecure. So that is an interesting trade-off here. It means that security is not about perfection. You never have perfect security. Security is all about trade-off. You have the theory, but you also have the theory context, and you have to meet in the middle, have a solution that works within the theoretic, within the practical constraints, not just pure theoretical definition. How can we support weekly auction here with the protocol that I described? With exclusive privacy, because everyone can learn the extra bid information, so that makes it easy. At each deciding position, if you are the bidder who submits one, then you know whether or not you have lost. If you have lost, you learn nothing. But if you are still in the race, that you know you have supplied one to that bid position, and you know one extra bid information, whether or not you are the only one in that, you are the only winner, or there's a tie, or at least another bidder has supplied one in that Boolean OR gate. If you are the only winner, then you don't need to do the rest computation. You can simply step forward and say you are the winner, and you reveal your commitment. Then everyone can verify. And if you are the only winner, then you declare yourself and you step aside, because there's no point for you to continue for the rest computation. So for the rest bidders, they reset the output of that particular bid position and make it long-deciding position, because you exclude the winner, and they continue executing the rest of the protocol. Then they know they can obtain the second highest bid. What you get is that at the end of the protocol, you know who is the winner and what is the second highest price. Everything else is secret, and you don't know the highest bid. So this actually gives you the best protection overall on the privacy. So you have a pragmatic definition on privacy. So you allow each bidder to learn limited information, and based on that, you end up a protocol which actually gives you better privacy protection. And in this case, no secret channels, everything is public, and everything is public verifiable. If you are the seller, you can verify the whole process, the transcript, and you know that the result you get from this protocol is correct. So the revenue you get from this auction process is correct. No need for any auctioneer, adaptive, If there's a tie, you can easily resolve the tie. Most importantly, you have the linear complexity with respect to the bit length. Usually 20 bit for the bit price is more than sufficient. And it gives you reasonable trade-off for the privacy. In order to guarantee your privacy, you simply need at least another bidder who is honest, so you hide in the cloud. So the conclusion from this is that now we actually show it's possible to implement this weekly auction without auctioneer for the first time. You can implement a weekly auction on a blockchain, for example, a Ethereum blockchain. Here, blockchain is nothing special here. It's simply an implementation of public bulletin board. So you write a smart contract, which is public and everyone can see it. As bidder, you encrypt your data and you publish the data on the Ethereum blockchain. And then this smart contract will do the verification and compute who is the highest bidder. So this is, we think this is totally doable. And if you can implement this smart contract on the blockchain, then that means you can do the weekly blockchain, you can do the weekly auction on the blockchain. And this will be the first time you can do the weekly auction without auctioneer. So to us, we think that is actually very exciting, but still we need to implement it. But at least for now, we think this is possible. That's the end of my talk. I hope I'm still in time. Thanks for your attention. I'm happy to answer any questions.
So from participant and any question is there, you can directly ask or you can put in the chat box. Participant, you are having any question, you can put in the chat box or you can directly ask.
Sir, there are questions in the chat box, sir. The question is, sir, what are the biggest cybersecurity threats right now by Arjit De Sarkar?
That's a big question. I wish I would know the answer. From my perspective, I'm from an engineering background. And my take on this question is that the biggest cybersecurity threats are that the systems now are too complex. And when it comes to IoT and cybersecurity, cyber physical systems, you have too many complex designs. And the requirements are changing constantly. The environment is changing constantly. So you constantly change your implementation, adding more features. And you often do it in an ad hoc way. Because there's a lack of standard, the standardization doesn't catch up with this dynamic change of the landscape in IoT and in the cyber physical systems. So you end up with lots of systems which are so complex. Because the systems are complex, then they are so easy to be broken. Complexity is the biggest enemy of security. So really, you should make the system simple by standardizing the implementation, standardizing the design, but that's not happening. So I would say the biggest cybersecurity threat now is complexity. Not too relevant to my talk, but that's just my understanding from a security engineering perspective.
Any more question?
Sir, right now there is no question, sir.
Okay. So if there is no question, thank you to Professor Feng Hao. So nice to meet you again because we have met in 2018.
Yes.
Feng, yeah.
For having me. I hope
yeah.
sometime
soon. Okay.
Yeah. Okay, thanks a lot.
Yeah, sure. Even you see, I am thankful to you from your busy schedule. You are able to giving the talk. You have agreed. Thank you.
Okay,
Thank you again. We will meet in the near future. And I also having discussed with that Tony also sometimes on the chat,
Okay.
WhatsApp chat.
Yeah.
Okay. Thank you very much for your valuable speech, Professor Pham. So our next speaker, Professor Ruxandra F. Olimint. Ruxandra Olimint is currently an associate professor with the Department of Computer Science, University of Bucharest, Romania, and an adjunct associate professor with the Department of Information Security and Communication Technology, Norwegian University of Science and Technology, NTNU, Norway. She has a background in both computer science and telecommunications. Her past experience in the telecom industry include almost 10 years with the Orange of Romania. Her research interests include privacy and security in communication networks. She will speak today on the topic privacy of subscribers in mobile networks, changes and challenges over time. So, Dr. Ruxandra, you are welcome to present your presentation. Start your presentation.
Thank you.
Thank you, Ruxandra. You can start.
Okay, so you should be able to see my screen now.
Yeah, it is visible. It is visible.
Okay, thank you for the invitation and thank you for the introduction. When I got the invitation for this talk, I thought about what should I talk about, and because the invitation came via my affiliation at NTNU, Norwegian University of Science and Technology, I thought the best thing to do is to talk about some of the work that I done as affiliated to NTNU. And that is also together, it's a joint work with Professor Stig Mjolnes from NTNU. And even if it's not necessarily there are not necessarily very new results, I think there are very hot topic today. So I'm going to talk about privacy of subscribers in mobile network, and I'm going to present a little bit how this changed over time. So going through the generation, starting from 2G, 3G, 4G, and finally going towards the fifth generation of mobile networks. So what is the motivation for this? This is really simple and I think straightforward for everybody. Almost everybody, at least in the urban areas, has a mobile phone today. So if we look at the statistics, only in India, the smartphone users is estimated to reach over 760 million in 2021. And overall, 3.8 billion users, while the estimated human population is, let's say, a little bit more than doubled. So everybody has a smartphone or uses a smartphone nowadays, at least in the crowded areas, in the cities or in the populated places. So what is about the mobile network evolution? I will not go into details here. I think most of you are already familiar with the technology. So 2G, 3G, 4G, and now the new 5G. Of course, 2G introduced the digitalization. Okay, so it makes the change from analog to digital, and then we have a lot of increasing bandwidth and low latency, and a lot of services that come over. when we talk about 1 to 4G, we can speak about people. When we go to the fifth generation, so 5G, we also introduce the things. Okay, so you already heard a lot even today about the Internet of Things. Okay, and this refers to 5G, let's say mostly. Okay, so what I'm going to do, I'm going to go a little bit from the 2nd generation to the 5th generation, and I'm going to talk about the security improvements. And I'm going to focus on the privacy of subscribers. Okay, so that's the focus for today. How this is put into place, so what are the mechanisms that are providing some privacy for the subscribers, the new ideas that come from generation to generation, the vulnerabilities that appear, because as we already heard, even today and in many other security talks, many times it's easier to attack a system rather than create a strong defensive system or secure system. Okay, so in order to do that, we need to know a little bit about the architecture of mobile networks in general. So this is a very general picture of the architecture of mobile networks. Basically, we have some user equipment. The user equipment can be the phone, can be a tablet, can be everything that the end user uses to connect to a mobile network. Then we have the access radio, the access network, okay, which is the connection of the user towards the network. So it's basically, we can think it very, very basically as the radio link to the network. And then we have the core network, which is basically the core or the most evolved part in the mobile network, where the switching takes place, where the authentication, let's say, of the user from our point of view will take place, and where the credentials of the users are stored and so on. And this is a very, very general view of the network. So what we're going to do is going to look a little bit into more details into different generations of networks. So if, for example, we look at the 2nd generation, and in the 2nd generation, you probably know the most known implementation is the GSM, Global System for Mobile Communication. We have the mobile equipment that is called mobile station in the standards of GSM. And what is this mobile station or mobile equipment build-up, or what it consists in? It's basically a device, and it's a SIM card. So basically, there is the phone, and there is the SIM that it's placed inside the phone and allows us to connect to the network. Okay. And what is important for us, what I'm going to refer to here, is some information that is stored in the SIM, and it allows the user to associate to the network, to make use of the services that the network offers, and how it identifies the subscriber within the network. So here there are two things. First is the IMSI, which is a permanent identification of the SIM card. So it comes from International Mobile Subscriber Identity, and it's basically the identifier of the SIM, okay? And then a cryptographic key KI. That is just a notation. It's a cryptographic symmetric key that is stored within the SIM, okay? So basically the IMSI is the identity of the subscriber in the network, and KI is the cryptographic key that is going to be used for getting access to the network, for deriving other keys that are going to be used later on for encryption or other purposes. Okay. All this information, so the IMSI and the KI, needs also to be stored in the network side. Because if that does not happen, then the user cannot be authenticated to the network. So on the network side, they are stored in, let's say, a database that is called HLR in case of GSM. So it's a home location register. So for each of the subscribers of the network, there are this information, this ID, that is the IMSI, and this K, that is KI for a user I, let's say, the cryptographic key. Okay, that happens for GSM. Now, this IMSI, International Mobile Subscriber Identity, consists of 3 parts. The first one gives the country code. So the first 3 digits are representing the country where the operator that issued the SIM is coming from. And you have here some examples. For example, for India, the mobile country code can be 404 or 405, probably because the number of SIM card issued in India are so many. There are 2 mobile country codes. Okay, you also have some examples from Norway or Romania, 242 or 223. Okay, so basically these are the first 3 digits in the IMSI. The second part of the IMSI consists of the mobile network. So basically in India, and here I hope I took 2 operators that are known in India. I'm sorry, but I'm not familiar to that. Basically, if you have an IMSI for which the 4th and the 5th digit are 81, then it means that the SIM belongs to BSNL. If there are 44, it means that it belongs to SPICE. Okay, these are not the only numbers that are here. So of course, every operator has more digits that are associated to it. Okay, so for example, SPICE can have even 14 and so on. And then the last part of the IMSI is a number that identifies the mobile subscriber. So it's unique for each SIM card. And what is this? Why is this important for the privacy of the subscribers? Is because once the user owns a mobile equipment, okay, or a phone that is together with the SIM card, of course, in order to connect to the network, this IMSI becomes kind of one identification for the person. So basically, if you have the phone with you all the time, and somebody realizes that the IMSI has been seen in a specific location, they will say mostly for sure that you've been in that specific location at that time. If somebody wants to find out if you're in a crowded place, they can just try to see there is a phone that has your IMSI in that, let's say, square or area. If there is, then can say, okay, you've been there. If not, you've not been there. So because the mobile phone is something that the users are carrying all the time with them, it makes the phone and the IMSI become kind of an identity for the user. Of course, this is not all the time happening, but we can consider up to some extent that this happens. Okay, so this is the IMSI that we talked about. So it's the identification, the permanent identification of the subscriber. And we also talked about the cryptographic key, that is the key that is stored in the SIM and in the core network. But then there is something else that comes into place, and this is the TMSI, the temporary mobile subscriber identity, which, as the name said, is a temporary identifier. And its role is to get the place of the IMSI so that the IMSI is not so exposed. So as I was saying before, if you're using the IMSI all the time, or your device is using the IMSI all the time, it's easily to identify or to track a person or to see where it was or where it moved, okay? While if this IMSI is usually changing, let's say periodically, or when some specific things happen within the network, then it might be more difficult to make a connection between the IMSI and the temporary identifier, and having more temporary identifier in times might make you less trackable in time. Okay, what happens in GSM? Basically, to authenticate to the network, there is a challenge response mechanism. And here I will not go too much into details. It is a challenge response mechanism where the mobile equipment, or the mobile station, as it's called in GSM, it sends its identifier to the visiting network. The visiting network can forward further to the home network if this is the case. And then, based on a random challenge and the key that resides in the SIM card of the user, the mobile station will compute a response. This response is going to be checked if it's the expected response or not. If it's the expected response, then the user is allowed, the subscriber is allowed in the network. If not, not. And here is where the TIMC comes, let's say for the first time. So when the user authenticates to the network, the mobile equipment gets back, or the subscriber gets back a TIMC that is going to use in the next communication with the network. So let's say for the first time we turn off a phone, there is not a temporary identifier associated, so the user needs to send its identifier and say, hello, it's me, I want to connect to this network. But afterwards, after the first authentication, let's say it's complete, it gets a temporary identifier, and next time it needs to communicate to the network, it will do it via this temporary identifier. Okay. The same thing happens in other network generation of networks. So, for example, in LTE, it can be considered the fourth generation of mobile networks. Here we have a small change in the architecture. I will not go too much into details. We have some smarter antenna that can even communicate between themselves. We have the user equipment that also has the IMSI and the cryptography key K. The same are also stored in the database of subscribers that is in the core network side. And again, the IMSI maintains the same structure. So it consists in a mobile country code, a mobile network code, and a unique identifier for each SIM card. In the fifth generation, things change a little bit in terminology, in the sense that the IMSI is now called the SUPI. In fact, SUPI, or subscription permanent identifier, can be a little bit more than the IMSI. It can be the IMSI or something else, depends on the case. But for us, it's going to be basically the IMSI from the previous generations. We also have the same key, so each subscriber has a key, a symmetric key that is stored in the SIM. The same key is also stored in the core network in a unified data management or unified data repository, which contains basically all the SUPIs and all the keys of all the subscribers. And in addition, it will contain something else. It will contain some private keys of the home network. So the novelty that arrives in 5G, or is introduced in 5G, is that now the network owns some pairs of public private keys. So the home network will have a public key and a private key, or better said, like a set of these keys. And we will see what this is used for later on. So what is the role of the temporary identifier? I already said, but it's important, so I'm going to say that one more time. Basically, the IMSI can become a kind of identifier not only for the phone, for the subscriber, for the SIM, but also for the user. Okay, so you as a person, if you have the phone all the time with you, it can kind of identify you. And as I already said, and again I repeat, basically whenever there's nothing else that the user equipment can use in the communication with the antenna, let's say, okay, in the access network, and further in the core, it will use this permanent identifier. But whenever it has a temporary identifier, it will use this temporary identifier as a way of hiding the permanent identifier. Okay, so it's going to use one temporary identifier. After some time, it's going to be changed. So it's going to be used another temporary identifier and so on. And of course, this kind of assumes a synchronization between the user equipment and the eNode B, or the core network, let's say, depends on the network that we are. Because of course, the network needs to understand this temporary identifier, who it belongs to. So it needs to know that this temporary identifier, it belongs to this specific IMSI and not to the other one. Because otherwise it cannot identify the subscriber, yes, the user equipment in the network. And what is the problem here? The problem is that there is the possibility that the network, the core network, loses this synchronization. And if this synchronization is lost, then the only thing to do is, okay, it asks for this permanent identifier. So it sends back to the user an identity request saying, I'm sorry, I don't know who you are, even if probably you gave me your temporary identifier before. I need your permanent identifier so that I can identify you in the network and then allow you access or give you access to the services that you're supposed to have. And then what is the user equipment doing? The user equipment is replying with the permanent identifier. And this is what happens up to the 4th generation of mobile networks. And this is something that was assumed in the standards. So in the 3GPP technical specification 33401, it's written that this represents a breach in the provision of the user identity confidentiality. Okay, and why is that? Because the network can ask for the permanent identifier because of a true reason, but it can also ask in case of malicious attacks or malicious adversaries, where, for example, a fake eNode B can ask the identity of the user equipment, and then the user equipment will just reply with the identity. And this is what is called the IMSI catcher. And it's called like this because, of course, what it's doing is just catching the IMSIs. So it's asking to get the IMSIs of the subscribers, and it gets back their values. And they exist in the real world, and they are also used in good purposes, so not only bad purposes, for different situations. Of course, this is, if we consider it as an attack, this is a malicious action. And malicious actions within the telecom industry are not considered to be of a very high impact. So if, for example, we look at the annual report in telecom security incidents from last year from ENISA, ENISA being the European Union agency for security, we can see that the malicious actions in a telecom network, or what it has been reported, it's only 5%. Okay, this is not looking at our particular case of IMSI catcher, but the biggest problem here are not the adversaries, the malicious adversaries, but are the system failures, as you can see, or the human errors, or so on. So maybe also because of this, and from some other specific reasons, like, for example, trade-off between security and efficiency and so on, this has not been considered from the beginning to be introduced in the standard. So like protection against these types of attacks. So what happens as we go from the 2nd generation towards the 4th generation? Of course, the security improves. And I'm not speaking only about the privacy of subscribers here, but in general. But also the technical capabilities at large scale increase. And what this means, it means that while in the 2nd generation, the attacks were simple, like the idea, it was more difficult for adversaries that didn't have access to the tools to put them into place. While as we go towards the fourth generation, of course, the attacks must become more advanced because of the cryptography, because of the security protocols that are set in place. But it's also easiest to obtain the tools in order to set up this kind of attacks. And what I mean by that, what a simple attack means. For example, in GSM, the simplest thing to do, it was to take a fake BTS. BTS is like the antenna in GSM, and place it closer to the user equipment. And then if the signal strength was better for the fake BTS, the user equipment was just deconnecting from this BTS, the genuine one, and was connecting to the fake BTS, and then was giving all the information that the fake BTS was asking for. When we move forward towards 4G, this doesn't happen anymore. So if you just place an antenna, fake antenna, a fake E-node B, closer to the user equipment, then it will not directly connect to the antenna, to the new one, but you also need to do some more configuration and to trick the phone somehow to disconnect from the older antenna and come to from the real, from the genuine one and connect to the fake one. So the thing that nowadays it's easier to obtain the tools to set up these things. This has a good part and the bad part. So the bad part is that it facilitates attacks. So it's easier for somebody to mount an attack because it's easier to set up a fake base station. On the other hand, it's a good thing because it also facilitates experimentation. So something that before it was possible only for the telecom companies or for big association of standardization or so on, now it's also available, let's say, for academic level. So we can now try to do some experiments within the academical community, and this is due to some software that is open source. And I gave here only a few examples: OpenAir Interface, SRS-LTE, or OpenBTS, that are basically emulating the mobile network. And also due to quite low-cost equipment, software-defined radio that allows to emulate the base stations. Okay, so how this works, or how can you emulate, let's say, an E-node B, if we talk about 4G, the fourth generation of LTE, is basically with a computer running this open source software, and then with a software-defined radio, as explained before, that is emulating the tower, the antenna. So basically with this, you can emulate the network, the mobile network, so you can try to set up an IMSI catcher, let's say, okay? Or you can argue about the security of a mobile network from all different perspectives. I'm going to talk a little bit about our IMSI catcher, or how we did to implement this practically. So basically, the user equipment was connected in the network, and then we had to make it disconnect from the network and connect to a fake target, which we call E-node B collector. And collector is because it basically collects the IMSIs. Okay, so it's going to be the IMSI catcher. But in order to do that, I said at least in 4G, it's a little bit more difficult. So it's not straightforward that it was in GSM. So we need to make him first disconnect from the genuine network, okay, so from the mobile operator to connect to this one. So in order to do this, it's possible even without, but it's easier with, you can use a jammer. So you basically jam the communication, and then the user equipment will connect to the collector, okay? And in order to do that, at least for 4G, there are some other configuration you need to do. Otherwise, the user equipment will not go to this collector, so to the fake E-node B. It can connect to some other E-node B that are belonging to the network. because you might know that usually it's like an overlapping in the cell coverage for mobile operator. Okay, so in order to do this, of course, you need some specific configuration for the fake eNode Bs. You need to put the same mobile country code, the same mobile network code, because the user equipment tends to connect to the home network, so to the network that the SIM belongs to in general. And of course, you need to put a specific frequency, a good frequency that is high in the list of priorities. Otherwise, the user equipment will connect to another tower that has a better priority, or it's on a frequency with a better priority. For the hardware, what we used in our experimentation was the A2B200 mini and some antennas, some normal computers. You can see everything here. Of course, there can be 2 desktops or 2 laptops, or it doesn't matter. These are the SDRs, and then some mobile phones, okay, or mobile terminals. And for the software, we've used OpenAir interface. We also did some simulation with the SRC LTE in the passive adversarial model. So what's important here, or what are the results of this? It's basically when there is an identity request coming from the network, where the network, in our case, the fake eNode B, asks the IMSI, the identity response comes with this IMSI, so the identifier, the permanent identifier of the subscriber, in clear. Okay, so here it's just hidden, but here, in fact, you see the exact IMSI. So this is just a part of a capture file. Okay, and this was done at that time basically with no change in the software, very, very basic code in the software. And then we improve this and we say, okay, what's happening when you just leave it like this? The thing was the fake tower was giving back to the user equipment after asking the identity, collecting the identity, it was replying with an illegal user equipment. So it was replying back with an attach reject message. That means you're not allowed to connect to my network, but that was the fake network, with this specific cause 3. And that means illegal user equipment, meaning that until the rebooting of the device is not connected in the network anymore. So that means that if there was an IMSI catcher in the nearby and your phone tried to connect to it, then you remain without connectivity unless you reboot your phone, and then it gets to connect again in the mobile network. But what happens if you change the causes? So for example, if the fake BTS, instead of replying in this attach reject message with the cause 3, it replies back with the cause 7, EPS service is not allowed, it means that the user equipment will not connect to the LTE network anymore. So what it's going to do is going to do a downgrade to 2nd generation or 3rd generation, okay, depending what's in the coverage of that area. And why is that bad? It's bad because then you can set up in place more powerful attacks that were possible in 2G and 3G, okay? Or another scenario is like, okay, the fake tower replies with cause 15, no suitable cells in the tracking area, which means that the user equipment will immediately reconnect to the commercial network. So it means that once the IMSI catcher was in the place, the user connects to the IMSI catcher, it gives away the permanent identifier, but then immediately goes into the commercial network. So basically for the user, that's difficult to realize that something happened there. So unless you're in the middle of a phone call and you see that it's failing, you basically don't look at your phone every time to realize that for 2 seconds your phone was not connected in the network and realize something goes bad there. So there are a lot of publications about IMSI catcher. So a very simple search on Google Scholar points out thousands of publications in about IMSI catchers. I put here only a few that were, let's say, really at the beginning and very interesting to read. Or if it's interesting, they don't belong to us, but they are also very nice to read. What you need to know, that's not the only thing that can happen, let's say, from the perspective of the privacy of subscribers in the mobile networks. And there are many other things that can happen. And we can look into the privacy of subscribers from many different points of view. And one way to look into it is the paging. I don't know how many of you are familiar with the paging. Basically, the user equipment is not all the time connected to the network, but it's kind of entering an idle state. And in order to be woken up from this idle state, it's received these paging messages. So whenever somebody calls you on your phone, you get the paging message that contains an identifier of the phone. It's broadcasted into the network. And if the user equipment realizes, okay, it's my identity, being it temporary or permanent, it's waking up and it knows that something needs to come for him. So it will receive a message, it will receive a phone call or something like that. So these are basically the paging messages that are broadcasted, and that contains some information. And that information needs to tell the mobile equipment, not the equipment, but the user equipment, it needs to say, okay, it's intended for you or not. So it needs to contain this identifier, which usually should be the TIMSI. And here there is one example about how you can find the temporary identifier by decoding some messages, broadcast messages that are sent by the network. In the worst case scenario, here are not the temporary identifiers, but are the permanent identifiers, which of course in general should not happen. But if somebody captures these messages, which I said there are broadcast and they're broadcasting clear, it can just decode them and find, okay, why is the network searching for a device in this specific area? It means it's either here or it was here before, because usually the network is not sending these paging messages everywhere. So for example, it will not send everywhere in India, but it will send in the last place that it's seen you. And if you don't reply there, you as a user equipment, then it will enlarge the area that is broadcasting these messages and so on. But the first thing to do, because of efficiency reason, it will just send it in the specific place that you've been before, or it's expecting to find you. So again, there are a lot of publications about paging as well, and about paging attacks, and that's just another example that can be in connection with the privacy of the subscribers. What happens in 5G? I was saying that the SUPI is considered like the IMSI, like it was in the previous generations. So the thing in 5G is that in response to the identifier request message, the user equipment will never send this identifier, the permanent identifier, SUPI. So from this point of view, in 5G, we have an improvement in the privacy of subscribers. And this had not been adopted before and could have been adopted in 5G because of various reasons that we don't discuss here. But what happens if the user equipment will never reply with the identifier? What happens when the synchronization is lost? So we have the same problem that we have had in the previous generations. So what happens if the network doesn't know the permanent identifier and it cannot find it based on the temporary identifier that the user equipment provides? So what happens is that it is sent in an encrypted form. So basically the subscriber permanent identifier, it is encrypted in a concealed identifier called SUCI that is going to be sent over the network. And here is where the asymmetric encryption and the home network public and private key came into place. So I was saying that as a difference from the previous generation, in 5G, we will now have some pairs of keys, public key, private key, that belong to the home network. So the home network public key and the private key. And of course, the symmetric key that is coming from the second generation of mobile networks. So this public key, of course, being public, it is known to everybody. So even the user equipment can have the public key of the home network. So what's happening? It's basically a key generation or a key agreement between the user equipment and the core network or the home network, after which a new key is going to be set in place, and this key is going to be used to encrypt the identifier of the user equipment. So basically how this works, basically at the user equipment side, the user equipment is using the home network public key. It generates a public key and a private key of its own. And here is coming to place a new facility that the SIMs, the USIMs, have in 5G to generate randomness. So it can generate a pair of public-private key, ephemeral pair by itself. So it's using the private key, his own private key with the public key of the home network in a Diffie-Hellman key exchange. And from this, based on a key derivation process, it's output an encryption key that is used in a symmetric algorithm, let's say AES, to encrypt the identifier. And this encrypted identifier is sent over the network. What's happened in the home network side? The home network, of course, has its private key, uses the public key that was generated by the user equipment, and this is ephemeral, so every time it's going to be a different one. It uses the same type of key derivation algorithm in relation with the Diffie-Hellman key exchange. It gets the encryption key and it decrypts basically, because here we have this symmetric encryption, what this SUCI, the concealed identifier that it receives, and gets the permanent identifier. If you look into the standard, you can find this in the standard as well. I just went for another representation from one of our papers because it was containing both the user side and the network side. But if you look into the standard, you will see what happens at the user equipment side. So basically it's the same, is the generation of the ephemeral key pair, the public key and the private key. Then the private key of the user together with the public key of the home network is used in this key agreement, and then it derives the key. And this key is used in a symmetric encryption for the SOTI. Okay, there is even a part of integrity protection that I didn't talk about, but we will leave it out for now. And this is called IES, so elliptic curve integrated encryption scheme, because basically what happened here is elliptic curve based, and this is because of efficiency reasons. Okay, we know that the cryptography on elliptic curves is more efficient than let's say on other groups. And the same you can see at the home network side, so I'm not going to go over that again, but it's the same, the agreement. Now we're in the network part, so the network knows the private key, of course, because it's a home network. It gets this ephemeral public key of the user, it derives the key, and then it's using for a symmetric decryption from the concealed identifier to get the permanent identifier. What is the problem here? First, there are these computational costs and difficulty, and difficult management caused by the public key crypto. And this is somehow left at the responsibility of the mobile operator. In the sense that there is the possibility of having a null scheme, and the null schemes means that this encryption in fact does not take place. Okay, so again, if we look into the standard, it's possible that the user equipment generates a SUCI using the null scheme only in the following cases. If it's an emergency situation, okay, but also if the home network has configured the null scheme to be used. So if basically the network operator does not want to set into place or cannot put into place this protection, then the null scheme remains into place, and then the identifier is still sent over in unencrypted form. Okay, that means null scheme, basically the identifier is not encrypted, so it's sent in clear. And of course, not much time passed by until not only in academia, but also in the press appeared information about 5G IMSI catchers. Or 5G SUPI catchers, because as I said, SUPI is like the new name for the IMSI in the 5th generation, saying, okay, this is possible. And it's possible also because of what I pointed out before. So maybe one downgrade to previous generation, or maybe the introduction of a null scheme. And I'm not going to go into this specific implementation here. I'm just going to give you one example where of a paper where they showed that it's possible to have to make the user equipment think that the network capabilities are not accepting other protection rather than the null scheme. And this is basically because some leakage, let's say, or some missing of integrity protection for some messages within the communication. And why I wanted to point out this paper is because they give a nice idea about how to approach attacks or vulnerabilities, or how to reason about the security of mobile networks in general by using a formal framework, so a formal method, and not just by trial and error or something like this. And I know you had Professor Elisa Bertino invited for one of the previous talks, even for your seminar, so probably she already gave you more information about that. Unfortunately, I did not see that one, but I've attended another lecture she gave as a keynote speaker to some other conference end of September last month, September, where she was pointing out the necessity of looking into the security of the 5th generation, let's say in specific, but also mobile generations in general, from a formal model point of view. Okay, and this will conclude my talk. Thank you for your attention. And if you have any questions, please feel free.
So participant, any questions from your end? Participant, if you are having any questions, you can directly ask, or you can put into the chat box.
Hi, can I ask one question?
Yeah.
Oh, thanks for the talk. Very informative. I really like it. So in the 5G, you mentioned using all these public keys and the PKI. How the 5G are going to manage the PKI infrastructure, given that it's a very complex infrastructure to set up and manage, and all these countries, they don't trust each other.
Okay, that's one of the, thank you for your question. That's one of the things that stopped, let's say, the public key infrastructure or public cryptography enter into this field before, up to the 4th generation. And seriously, I don't know how to answer to this question, because even in standard, or at least the one that I based my talk on, the security architecture, this is left outside of the discussion. So everything is kind of left into the network operator side. And this, as you say, it's really, let's say, easy to do when you don't talk about roaming, because you can put the public key of the home network into the SIM card. And when you give it to the user, you give the SIM card together with the public key. But what happens when you're in roaming, then everything needs to go towards the home network again. So even if you can compute everything using your home network public key that it's already, let's say, provisioned in the SIM. And then it's the visiting network that has to connect the home network and settle out everything that needs to be done in order for you to get access. So it is something that is introducing a lot of problems. And that's why it was not something that was intended from the beginning. The problem is that a symmetric solution to this doesn't really exist. Or there are some approaches to the problem, this problem of private identification, but they mostly assume some very strong assumptions, like not using synchronizations or things like that, which you in practice cannot really assume.
Yeah, thanks a lot. I think probably one of the assumptions is that Trump need to trust case from China, and that will be a big problem.
I'm sorry, I did not hear so well. I think somebody, if you can repeat, please.
Oh, no, and not a question, just a comment. I think one of the problems will be the trust problem. So if Donald Trump has to trust the certificate signed by Chinese telecom, that will be a difficult thing to implement. Something for the future.
True. Yeah.
Thank you.
Thank you.
So there is one question from Tosun Hajra. Can we use blockchain to authenticate 5G user?
I don't know what would be the benefit to use blockchain in this. So blockchain has this good name, let's say, lately to be used for everything. But we need to think about what's the benefit of using it for something. So what would the benefit of using the blockchain for 5G users? That's the thing we should ask. Now depends what we're thinking about. If we think for the mobile networks, most probably there's no point to do that. If you think for other like IoT devices, constrained devices, or other things, you also need to consider about the capabilities that they have. So blockchain, it introduces some computational power that you need to have at the end device as well. Depends how you use it, but usually and then it's even bringing more complexity. And as Professor Howell was saying before, when you have complexity in your system, you also have a problem in your system. So all the time you need to think, okay, what's the real benefit that it's bringing? It's really necessary that I need to use it. Can I do it in another simpler way?
And there is another question asked by Akash Sandar. In 5G, is it true 1 million IoT device can be contact in per square kilometer? What is the paging occasion problem in 5G?
Okay, so I cannot respond very well for the technicalities of the 5G. I'm mostly into the security part of 5G. But it is true that there are a lot, one of the ideas of 5G is to leave a lot of devices to be connected in the same time. And how they do that, they do it with small antennas that are connected very close to the devices, right? So basically the coverage area is really small, so you have a very high bandwidth, so you can use really a lot of this. So you can have a lot of devices and very, very low latency and so on. The paging occasion, it's because I talked about paging in my talk before. It's how often does the network send these paging messages? And I'm happy that it was brought up to the discussion, because it's also a nice attack, let's say, of vulnerability on 4G and also 5G based on this paging occasion, because the paging occasion is somehow defined based on the IMSI. So you compute it based on these numbers, and then it can give you a way of coming back and building like an oracle to kind of attack the privacy of the subscribers again. So here I suggest you to have a look at the torpedo attack. It might give you more insights of the paging occasion, how everything works.
So Prem Kumar, is there any question or participant? If you are having any question?
Till now, sir, all the questions have been answered.
Okay.
Yes, sir.
So thank you, Ruksandra, for your valuable speech. You see, Professor Elisa Batino, he has given the talk on 26 September in our webinar. She has given the talk on security, privacy, and safety in the net IoT.
Yes, I saw that.
She has given the talk in our webinar, security, privacy, and safety in the IoT.
Yes.
Okay, thank you.
I mentioned her because I saw it was one of the previous speakers, and
Yeah.
her work is related to the field, so it was something that was really worth mentioning.
Thank you.
Thank
you, Rudaksha, for your valuable speech.
Thank you.
So from participants, any questions? Because you see, we are having now Professor Goldman also there, Professor Howe, and Professor Dr. Rudaksha is also there. So if you have any question, you can directly ask. Otherwise, you will go to the closing ceremony. So probably there is no question. So from speaker end, can you say about that this on your webinar from the speaker end? Professor Goldman or Professor Howe and Professor Rudaksha from the speaker end, can you say about this webinar? Just few words.
What did you say? I didn't catch that.
From your end, because you see, you have organized the many webinar. You have started about this is the 11th one. So from your end, can you suggest what is the benefit if you organize such a webinar in future? Are you getting, Professor Howe?
You mean any suggestions or?
Suggestion.
No, to be honest, I haven't actually looked at previous seminars, but I like the way you choose topics for the 3 talks today. I think all 3 different areas. So I really like this variety. So and you put that on YouTube, so make it public.
Okay.
Yeah, you have done a lot of effort. So congratulations, that's a really good effort.
Okay, thank you. So anybody else can say about?
The previous seminars, are they also available on the YouTube?
Yeah. They were all are available in the YouTube.
Okay, thanks for doing that.
Okay. Because you see, our honorable Vice Chancellor, he is also suggesting for this pandemic situation, if we organize the such type of event, that will be benefit for the research community. So Thank you all. Thank you all the participants for attending this webinar. And our sincere thanks to all three speakers, Professor Goldman, Professor Howe, and Dr. Rudaksa. So from your busy schedule, even we are able to spend some time for our research scholar and research community. So our hearty gratitude goes to you all. So we are also thankful to our Honorable Vice Chancellor for his continuous support and encouragement to organize such type of events and for the betterment of the students and research community. And my thankful goes to the Prem Kumar. He is the webinar member of the webinar team. He has communicated all the things to the all speakers and all participants. So last but not the least, you see that webinar is organized by the Department of Information Technology, Maulana Abul Kalam Azad University of Science and Technology, and in collaboration with Islamic Science of Technology, Islamic Science of Technology, Jammu and Kashmir. So our sincere thanks to all participants and all speakers. So if you organize in near future such type of events, we will expect the help from your end also. So thank you all. So we are going to the closing the session.
Thank you for the invitation
Yeah.
and an interesting event. And good luck with your next iteration.
Okay, thank you all.
Thank you for the invitation.
Thank you all.
Yeah, thanks from me. So I think it's very successfully organized.
Yeah.
Thanks a lot.
Okay, thank you.